Yeah, good morning my dear students. Today I am going to discuss the types of vibrations taking place in IR spectroscopy. So what are all the various types of vibrations taking place in IR spectroscopy? In the last class we have discussed about the fundamental vibrations, basically the stretching vibrations and bending vibrations taking place in infrared spectroscopy. So today we are going to discuss the various types and how we are categorizing them in a detailed manner with some examples. As for example, the various types of vibrations, the first important vibration is fundamentally IR active vibration. The second is IR inactive vibration. The third is degenerate vibration, and the fourth type of vibration is very weak vibrations. The fundamentally IR active vibrations are nothing but stretching and bending vibrations, which we discussed in the last class. IR inactive vibrations are basically Raman active vibrations, which is concerned mainly the symmetrical stretch vibration. Whatever the symmetrical stretch vibration is there, they are called as IR inactive vibrations or Raman active vibrations. What do you mean by degenerate vibrations? Degenerate vibrations means in molecules like gaseous molecules like carbon dioxide, the out of plane bending and the in plane bending occur at 666 centimeter inverse. Okay. That means both the bending vibrations takes place at one particular wave number 666 centimeter inverse. So both IR active but only one absorption band is seen. That means we should get two bands for both in plane bending and out of plane bending, but due to degeneracy of the vibrational pattern, we are getting only one absorption band at 666 centimeter inverse that is applicable for both in plane and out of plane bending vibration. That is why these vibrations are called degenerate vibrations. The fourth important vibrations are very, very important and having more significance in the interpretation of the molecules. So they are very weak vibrations. They are also called as additional vibrations. What are the various types of additional vibrations? There are three different types of additional vibrations. One is called overtones. We also call them as harmonics. The second one is called combination bands. And the third one is called difference bands. These are the various types of very weak vibrations or additional vibrations. Before going to discuss about this additional vibration, you should know that suppose if you have the ground state here nu 0, then V1 is the first excited state, vibrational first excited state is V1, then V2, V3, these are the next higher excited vibrational excited states, right? So the fundamental transition from the ground state to the first vibrational excited state is making with the help of fundamental transition. After that you will be having the higher vibrational transition, that is V2 and V3. So basically the most of the vibration, fundamental vibrations like stretching and bending vibrations will be coming from V0 to V1, and the higher states, the higher energy states, we will be getting additional vibrations. They are V2 and V3. Those vibrations are basically the weaker absorption bands, and at the same time they are the higher energy state vibrational patterns. They are called as overtones. Is it clear? So this is all about the diagrammatic explanation for your various additional vibrations here. Now we will discuss individually about the various additional vibrations. The first important additional vibration is overtones. We call them as harmonics. What are these harmonics? Absorptions occur at integral multiples of the frequency of fundamental absorption. What they are telling? Absorptions occur at integral multiples of the frequency of fundamental absorption. Suppose if the fundamental vibration is nu, the additional vibration is coming as 2 nu or 3 nu. This is the simple example here, right? If the fundamental absorption frequency is nu, the additional vibrations like overtone will be appearing as either 2 nu or 3 nu. That means they are coming in the higher excited states, higher energy states, but those bands are weaker absorption bands. That is a very important aspect, right? And they have some significance because these fundamental vibrations are mostly appearing in the mid-IR region. They are mainly appearing in the mid-IR region, whereas most of these overtones are appearing in the higher region. They are in the near IR region, right? So the fundamental vibrations are appearing in the mid-IR region, whereas the overtones are appearing in the near IR region, right? Now I can give one example for these overtones. Carbon-hydrogen stretching of alkane, the fundamental vibrational pattern or the stretching vibration will be coming at 2960 to 2870 centimeter inverse, especially in the mid-IR region. Now where the overtones will appear, they will be appearing in the higher vibrational frequency, that is in the near IR region. So first overtone, the overtones you will, for a single stretch molecule, you will have different overtones. You may get for one particular thing, you will be getting one overtone. In some cases for the same stretching vibration, you will get two overtones or three overtones also, right? So what will happen? This is the fundamental stretching vibration. the first overtone will be appearing in the range of 1700 to 1730 nanometer, not in centimeter inverse. Okay, so centimeter inverse means it will be coming in the near IR region, maybe from 12,500 to 4,000 centimeter inverse. Within that range it will come. And the second overtone will be coming in the region of 1150 to 1170 nanometer. So most of the fundamental vibrations are coming in the mid IR region for drugs and organic molecules. And the near IR region, you will be getting their additional vibrations such as overtones. Now, the next important thing is that combinations. Combinations are also called as beats. In music, we are using the terminology beats, right? So, what is called combinations? Two frequencies of vibration coupled to produce new frequency. When two frequencies of vibration, when they couple together, they will produce a new frequency. For example, nu3 is equal to nu1 plus nu2, right? Example for the combination band for CH stretch vibration and bend vibration. I already told CH stretching vibration will be coming at 2962 2870 centimeter inverse, whereas the bending vibration for CH group will be coming in the region of 1475 centimeter inverse. Now, when they undergo the combination band, so CH stretch and the bending vibration both undergo the combination, they will be seen at around 2000 to 2500 nanometer. So this is one of the classical example for combination band. Now what is the meaning of difference bands? Difference bands, if two frequencies couple such that nu3 is equal to nu1 minus nu2, the band is called difference band. So this is all about the difference band as such, right? Now when we talk about the various types of vibrations so far, we should know what is the law governing this vibrational pattern in infrared spectroscopy. The very important vibrational motion or the law governing is Hooke's law. Hooke's law is the very important law governing the vibrational pattern. So I can give an example here. Carbon, double bond carbon attached with, both the carbons are attached with first atom as well as with the second atom. So this is having a particular weight. This second atom is also having a particular weight. So this double bond is just like a spring. The bond length is just like a spring, right? So Hooke's law, what they states that the principle of IR spectroscopy is governed by Hooke's law. Two masses joined by the spring. If you are attaching two masses, the weight of the atom joined by a spring will vibrate such that the vibrational frequency is given by the terminology nu is equal to 1 by 2 pi root of f divided by mu. What is nu? Nu is the vibrational frequency, whereas f is the force constant or the strength of the bond, and mu is the reduced mass of the system. So what is this reduced mass of the system? Mu is equal to m1 into m2 divided by m1 plus m2. What is m1? M1 is the mass of the first vibrating body, the weight of the first vibrating body, and m2 is the mass of the second vibrating body. So this is the basic vibrational frequency formula by Hooke's law. But generally in case of infrared spectroscopy, we are using wave number. So nu bar wave number is equal to nu divided by c. What is c? C is the velocity of light. So therefore nu bar is equal to 1 by 2 pi c into root of f divided by mu, where nu bar is also called as the wave number of absorption maximum. So this is how we are getting the formula for the principle of IR spectroscopy using Hooke's law. Is it clear? The last aspect we are also going to discuss under this type of vibrational mode is vibrational coupling. This is a peculiar feature taking place. That is a coupling of vibrations. The vibrational coupling, when two bonds vibrating with a similar frequency and the bonds are much closer in a molecule. This is the criteria for vibrational coupling. When you have two bonds vibrating with similar frequency and the bonds are much closer in a molecule, then you will get vibrational coupling. The coupling vibrations, there are two possibilities for coupling vibrations or vibrational coupling. Either both the fundamental vibrations will interact with each other, you will get coupling vibration, or you will have one fundamental vibration interacting with one additional vibration, maybe an overtone, it will produce a coupling vibration. So coupling vibrations may be both the fundamental vibration or maybe one fundamental vibration plus one overtones. If the vibrational coupling takes place with one fundamental vibration with one overtone, then the technique is called as Fermi resonance. The technique is called Fermi resonance. I will just give an example for vibrational coupling. It is a classical example taking place with amide bonds. Most of the peptides or protein molecules contains this amide linkage, that is CONH bond, right? So in CONH, generally what is an assumption, what is our prediction? Expectation is C double bond O stretch vibration you will get and NH bend vibration you will get. There are two possibilities, or the expected wavelength or the vibration frequency will be appearing as either carbon double bond O stretch or NH bend will be expecting. But due to vibrational coupling, what will happen? Our expectation is different, observance is different, right? What is a different thing we are getting? The carbon double bond O stretch vibration is giving amide 1 band. The amide 1 band, there are two bands obtained for the vibrational coupling. One is called amide 1 band, the second one is called amide 2 band. The amide 1 band will be having corresponding to carbonyl stretch vibration, which is coming in the region of 1740 to 1630 centimeter inverse, whereas the amide 2 band will be appearing with NH bend vibration and carbon nitrogen stretch vibration. This is a very peculiar thing. This is mainly due to vibrational coupling. Our expectation is NH bend will be there, we are expecting. But here what will happen? Not only NH bend, also the carbon nitrogen stretch, both of them undergoes the vibrational coupling and they will give a specific band, amide 2 band at the region of 1630 to 1510 centimeter inverse. So this is a classical example for vibrational coupling. So this is all about the overview of the various principle behind infrared spectroscopy, and with the discussion with diatomic and polyatomic molecules, what type of mode of vibration taking place and what are all the types of vibrations taking place in the molecule and what is the law governing the vibrational pattern in IR spectroscopy, particularly with Hooke's law. This is all about the various principle involved in infrared spectroscopy. So thank you my dear students, thank you very much.